of the Romatschke lectures on modern relativistic hydrodynamics. So you have the floor.
Thank you. Okay, welcome back, everyone. So today's topic is hydro attractors. So in the first lecture, I built up the whole idea of transport descriptions as an effective field theory. In the second lecture yesterday, we used that for actual hydrodynamics, relativistic hydrodynamics. So we started out by saying that we can expand the energy momentum tensor in a power series where each of these correspond to basically zeroth order ingredients, first order ingredients, and so on and so forth. And since the energy momentum tensor is exactly conserved, truncating the gradient expansion, for instance, here will give us equations of motions that then we can solve to treat the dynamics of the system. So these have different names. If we truncate here, this is called Euler equations. If we truncate there, if we truncate at first order, we would get the relativistic version of the Navier-Stokes equation. At second order, you get a different equation, and so on and so forth. In particular, the equations of motion that you get here, so these are 4 equations of motion, and we can project on the time-like and the space-like part by using combinations of the flow velocity itself, u, and the space-like projector. So for instance, the projection with respect to the time-like velocity vector, if we sort of stick in, for instance, the zeroth order term here, sort of gives us an equation that, if we put the minus there for simplicity, so then we get an equation that looks like this. Which is just the relativistic analog of the usual equation of continuity. So in order to sort of get at the sort of hydrodynamic attractors, I will sort of talk about these equations. I will first talk about the concept at a sort of general point of view, so that we are treating these equations of motions without any sort of specific symmetries. But then I will sort of want to sort of show you what the attractors look like by sort of being able to calculate something rather than sort of waving my hand and saying this is how it's supposed to be working. So I will sort of assume a high degree of symmetry, in particular Bjorken symmetry, and explain what it is, so that it lets us actually calculate properties of the series and lets us sort of really get our hands on how we get to these hydrodynamic attractors in practice. So the last thing I want to sort of say is that so if we sort of go to, let's do this step by step. So this is sort of zeroth order hydrodynamics. If we do first order hydrodynamics, then you get the same left-hand side, but there's something non-vanishing on the other side. So in particular, you get terms that look like this. Eta over 2 sigma mu sigma mu. The sigma mu is the shear stress. And then in second order, you get higher order terms. And I said that we can use these higher order terms to our favor because this first order truncation, the relativistic Navier-Stokes equation, contains modes that propagate faster than the speed of light. So we can sort of repair that by the same trick that we already used at the diffusion equation, by sort of rewriting terms in such a way that we get an equation that sort of essentially looks like this. So we get an energy momentum tensor that sort of looks like this one, and we have the first order one, and then we sort of introduce, sort of rewrite it in such a way that whatever sort of is coming afterwards you put into a shear tensor pi, and also a box stress capital pi, and then these fulfill specific equations of motions such that pi mu would be equal to minus eta sigma mu, and then one of the second order terms we like to rewrite in such a way that it sort of couples back to our equations. So we would like to write it in terms of the pi that's appearing on the other side itself. And you can do a similar thing for the capital pi, the box stress. So this is just reiterating what I said last time. The advantage of this is that, so what are the consequences of doing this? The consequence of this says that when originally we had a mode here that was having a dispersion relation that said that omega is equal to k squared. This is the offensive mode that says that the dispersion relation grows quadratic in k, or the propagation speed sort of grows without bound. In this case, what you find is that there is the same omega here, but it gets sort of modified by the presence of an additional mode, which is coming from the fact that we have sort of written down this equation here. And that means that we get a quadratic equation for the dispersion relation, so that the speed of light, the speed of propagation is finite. And the price we pay, if you want to, is that we have now two modes in the system, and one of them has the property that omega, we call this omega NH for non-hydro. That is sort of the zero of this part here, and that's given by minus I over 4 pi. We have an additional mode in our description that is not present in usual Navier-Stokes, for instance. In that sense, if you define hydro by Navier-Stokes, this mode is not present in Navier-Stokes, so it's not hydro, so we call it a non-hydro mode. It's a very bad name. People have tried alternatives, but nothing really stuck. So we're stuck with the name of non-hydro mode, which is bad because it's never good to sort of have a definition of something in terms of what it is not. But here we are. Okay.
It's particularly bad since nowadays second order hydrodynamics is the standard way of using this hydro, and it's a part of that.
Right, yeah. So as Uli is pointing out, even more confusingly, second order hydrodynamics, this description here has this mode. So hydrodynamics has a non-hydro mode. Yeah, whatever. For historic reasons, this is how it's called. Good, but back to sort of the main line, I want to sort of get to the hydro attractors, and the easiest way that I can get there, I believe, is if I just, for the moment, stare at the Navier-Stokes equation, continuity equation, which is the line that sort of has the label 1 here. And now let me sort of talk about how you could potentially sort of find something that is an attractor in this system. Okay? So what is an attractor? An attractor is something that where sort of different initial conditions of the system, which can be very different initially, sort of go on and sort of find, if you want, the same trajectory that sort of will unify all of them at late time, such that if you wait long enough, arbitrarily far initial conditions sort of all converge to the same line. So this line then sort of we call an attractor for a certain basin of attraction. How would you find that? Well, if you just look at fluid dynamics as sort of water or something like this, you would say, well, different initial conditions give me very different sort of outcomes. So just looking at sort of different energy densities and sort of looking at how they evolve, you would not find directly what the attractor looks like. You can recognize the attractor only if you use the right scaling variables, okay? And the first thing we'll do is we'll look at what these scaling variables can be. And for that, we use this Navier-Stokes equation. And it's fairly easy. So we look at the Navier-Stokes equation. I want to sort of divide by this term here. And you might say, okay, that maybe is a bad idea because maybe we're dividing by 0 here. This combination, the total gradient of mu, that is sort of the expansion scalar. It corresponds to if you want, so if it corresponds to whether you can sort of, how far you can sort of compress the fluid. So for non-relativistic fluid dynamics, it's oftentimes a good approximation to say that the fluid is incompressible, in which case this would be exactly 0. Then I cannot divide by this. For relativistic fluids, incompressibility and Lorentz covariance don't work together well, okay? Because if you have something that you think is incompressible in one Lorentz frame, you do a Lorentz boost that sort of basically shrinks one direction, so you but get a compression simply from the fact that you say, okay, really what my description is Lorentz invariant. It's one of the symmetries that I wanted. So incompressibility basically never happens. The only exception to the rule is if the velocity itself is just, so the space-like velocity itself is 0, in which case you have hydrostatics, nothing is moving. That would be the only exception to the rule. Otherwise, you can assume this to be non-zero for relativistic fluids. So we divide by this, and we find that the equation we get sort of looks something like this. Oh, and okay, so I've set the bulk viscosity here to 0 just to simplify the discussion. But you can include it if you want. If I bring that on the other side, since I've divided by this is just 1. I bring it on the other side, so I get -1. And then I have plus eta sigma mu over 2 epsilon plus p total divergence of u. And then I will claim this quantity here, which I call A1, is an attractor in the following sense. If I look at the right-hand side here, in the numerator, I have something that is gradient squared because it's sigma squared. In the denominator, I have only one gradient, so it's gradient 1. So this quantity, if the gradients are small, will be small. So then for small gradients, whatever initial condition I take, this combination always will go to -1 if the gradients are small. So I claim this is a good scaling variable. It's a good scaling variable if I express A1 in units of this. And I will call this thing, I will call gamma to the -1, which is the inverse attenuation length, if you want so. But it's just a definition. So what does it mean? It means that if I wanted to, so if you took a system that was actually described by this equation, I claim you could take arbitrary initial conditions, gives you arbitrary energy density, arbitrary flow velocities. You look at this ratio here, A1, you plot it as a function of gamma, and then for large gamma, that is small, whatever sort of system you have, it has to go to -1 as gamma goes to infinity. Okay? So different initial conditions, whatever they are, all must sort of go to -1, basically because that's the way that I sort of define it. Assuming that the system is described by these equations, okay? So you would say, okay, I mean, that's, you're sort of doing something backwards. If we have these equations, that we have hydrodynamics, so of course we get hydrodynamics out. So the trick, of course, will be that we sort of take a system that is solvable in terms of some microscopic physics model. So take kinetic theory, or take a quantum field theory, or take ADS-CFT. But my claim is that we look at this scaling variable, we can check whether there are really sort of attractor behaviors that are sort of emerging if I sort of solve the actual system dynamics and then sort of calculate this scaling variable. You might say, why is this called A1? It's called A1 because it's the first attractor. There are other attractors that you can write down. In particular, there's an A2 that then will, in particular, feed on the bulk stress. But it is qualitatively similar to the A1, so I will only discuss the A1 in the form. Yeah. Sorry,
what are these divergences?
Right. So if it's rigidly rotating, yeah, I think the short answer is I don't know. You could potentially construct things where that also vanishes. I'm not sure if it's stable though. But I still think there are sufficiently interesting cases where the expansion scalar is non-vanishing. For once, where you set up things where it's vanishing, I don't know. So. Good. So this is basically where we are going. We have this scaling variable, and we want to sort of check basically what the scaling variable looks like when we have a system that we can actually solve. Okay? Good. Now let's do it. A1 in terms of gamma. So you need basically you need to scale the function and the x coordinates, and you need both. Yeah. So we want to sort of basically have a microscopic system. We can calculate it, but then we'll express it in terms of A1 as a function of gamma, and that's what we'll try to find attractor behavior in. So the simplification that I want to make is I want to sort of look at the Yorkian flow, which basically is a very clever invention. Sort of it comes up in the context of heavy ion collisions, for instance, where the idea is that if you have a heavy ion collisions, maybe we can approximate what's going on by saying that, okay, maybe the system is spatially homogeneous in the transverse part, so transverse to the beam axis, but then longitudinally we know the system is strongly expanding. So we just assume that it's expanding in a particular scaling way. So Bjorken flow says that, okay, the velocity with which the system is expanding is 0 in the two transverse directions, and it's z over t for absolute value of c smaller than t in the longitudinal direction. Okay? So it's expanding in one dimension, it's homogeneous in the two other directions. And because we prescribe what the symmetry is, this completely fixes the space-time, and then the discussion is, because it has so much symmetry, it's much easier to sort of do. A neat way of sort of making the problem tractable is to say that, okay, we can sort of calculate using this assumption, but we can do a trick. We can say that rather than we have a fluid that's expanding in one direction in flat space, we're going to take a fluid that's at rest in a space that's expanding in one dimension. Okay? So basically, we sort of trade this by doing a nonlinear coordinate transform that introduces new coordinates tau, e squared minus e squared, and psi, which is the arctangent hyperbolic of z over t. It's a nonlinear coordinate transform. It takes you out of the usual Lorentz symmetry group. It's a diffeomorphism transformation, and it sort of takes you to a system that is a space-time that has that is expanding in one direction, but it has vanishing curvature. So it's expanding but flat. Okay? And if we do that trick, what it means that in these coordinates, my fluid velocity u mu will then be given by u tau, ux, u by u psi. And in these coordinates, this fluid velocity is just trivial. So the system is at rest in the space-time that's expanding. So all the heavy lifting is done by the space-time, not by the fluid. And as a consequence, all the quantities, just the energy, only depend on time, which is not this funny time in this new coordinate system. So it's a beautiful sort of simplification. And what it means is then you can write down equations. So for instance, since epsilon is a Lorentz scalar that depends only on this t here, d epsilon, which as you recall is the co-moving covariant derivative of this. Since epsilon is a scalar, the Christoffels in the covariant derivatives don't do anything. So this is just v tau epsilon. But if we do the same thing for the fluid velocity, then since the fluid velocity is constant, any actual derivative will basically not give us anything because we're deriving a constant quantity. So the only non-trivial contribution from this comes from the fact that space-time is now non-trivial. There's a non-trivial metric. And this thing just becomes a particular combination of the Christoffel symbols associated with the metric on this space, which, by the way, G mu is diagonal, and it's given by -1, 1, 1, and tau squared. That's the metric on this space. So for this metric, it's fairly straightforward to calculate the Christoffel symbols, and you find that this thing is nothing else but 1 over tau. Little exercise in GR, calculate the combination of Christoffels for this particular metric. I recommend using some software because there are many entries in these Christoffels which are 0. Anyways, okay, good. This can be done. So, so this particular symmetry allows us to sort of greatly simplify the complexity of the problem. The equations get much easier, and then essentially what we have to do is we want to sort of solve equations of motion, and we want to do that for particular theories that, for instance, are not just Navier-Stokes, but some more complicated systems. One of these more complicated systems is something that we can sort of engineer. So we look at this equation here. It has an equation for the energy density where, okay, I said the dt, the covariant derivative just becomes the time derivative of epsilon. Then we have epsilon plus p. And then we have the covariant derivative of the fluid velocity, which is just 1 over tau. And then on the right-hand side, we have Navier-Stokes. We have this combination here, but we don't want to do Navier-Stokes. We want to do something maybe more complicated. So I'm going to write down a more complicated theory than Navier-Stokes, and we're going to analyze that theory, and I will call it a mock microscopic theory because it's not real microscopic theory like kinetic theory. It's something that is nonlinear and that can be solved, and it also happens to be useful for some other contexts. But yeah, let's just write it down and then discuss what it means. And pi over tau, and the second equation will be tau pi, tau pi, 4/3 theta over tau minus 1. So this is a theory where if I sort of put phi to 0, I'm basically back in the ideal fluid dynamic case. But if phi is non-zero, basically has a different differential equation that it fulfills, and this will generate some non-trivial dynamics that we can do. As a side remark, the phi here really sort of is Moronga's phi that was, I think, sort of introduced quite a number of years ago, and it's very useful in the context of discussing these sort of resum theories in the Bjorken flow context.
Is that the exact side component of the filter?
Yes. So basically this phi here is essentially up to a sign given by the exact side component of this shear stress. Good. So fine. But okay, so I will delete this left-hand side here because I need the space. But what I want you to remember from that part that I'm going to leave is that in these sort of second-order theories, we have this non-hydrodynamic mode which has had this dispersion relation omega is minus I over tau pi. Okay, so I'm going to use that later on in the fact. So I want to sort of make yourself a copy in your memory that says, okay, we have had this. Let's remember that as we go on. Okay, first things first. If we did ideal hydro, I claim that we can just set phi here to 0, and we get an equation of motion that's just given by dt epsilon is equal to minus epsilon plus p over tau. In order to solve this equation, we need one more information. We need to say what the microscopic equation of state is. That's an input. We cannot calculate that. We have to sort of say which system we want to describe. It is oftentimes useful to sort of use a so-called conformal equation of state, which says that the pressure has to be epsilon over 3. Conformal in this case means that the trace of the energy momentum tensor is exactly vanishing. That gives you this equation of state. We plug it in here. Epsilon plus epsilon over 3 is 4/3 epsilon over 3. We get this is equal to 4 over 3 or epsilon. And this is a differential equation that we can solve. So divide by epsilon, you get the derivative of the logarithm of epsilon. Yes.
How did we get the differential equation of phi?
Yes, very good question. So I said that I'll just write it down, but really what this is, what I had sort of said was this with some version of hydrodynamics, some version of second order hydrodynamics. That's what you can use to sort of get this equation. But right now, think of it as just something that I wrote down, which has the same characteristics of what I figured. So there's no sort of deep microscopic origin for this. It's a test.
What one can say about it is that it's an equation which says that phi approaches the Navier-Stokes value for tau on a time scale that's long.
Right. Yes. So as Uli was pointing out, so this equation, of course, has some physical meaning. It means that if basically if the time that you look at is long, this term actually sort of will settle down, and then phi will be given by this ratio here, which is nothing else but the Navier-Stokes limit of the shear stress, as you can recognize when you're an expert and have worked with this for many years. But right now, it's just an equation that I want to solve. In particular, I want to sort of take the limit where phi is 0. Then I said that, okay, this equation sort of becomes fairly simple. It just becomes d tau log epsilon is equal to minus 4 over 3 tau. And we can integrate this up. We can sort of bring the tau on the other side. So this has the simple solution epsilon over some initial epsilon naught. It's just tau over some initial tau 0 to the power of minus 4/3. So this is one solution of the ideal hydrodynamic equation in Gaussian symmetry. It says that the energy density drops like tau to the minus 4/3. For further use, I'm going to say that, okay, if we have this kind of equation of state, it also means that the energy density will be proportional to the temperature to the 4th power. Again, that's something that's thermodynamics of a conformal fluid in 4 dimensions. I will not explain where this comes from. You have to trust me on that. Basically, what it means is that up to some pure number factor in front of here, I can sort of choose this to be exactly equal to T to the 4. And then it means that my temperature for this system will be the 4th root of this. It will scale like the proportional to tau to the minus 1/3. Okay. Now, now I can sort of say, okay, that's fine. So that's sort of some limit. But now let's look at these equations in more detail and see whether we can actually make contact with my attractor variable that I've written up here. So this will be the case where phi is non-zero. If I want to calculate the A1 basically will be the derivative of epsilon. This is just dt epsilon divided by epsilon plus p. Well, it's just 4/3 epsilon times the gradient of u. I calculated that. That's just 1 over tau. So basically what we find is that the A1 scaling variable for this Bjorken symmetry is just given by this funny combination. And we can write it, for instance, as 3 over 4 times tau d tau log epsilon. That's the scaling variable. Yeah.
Another question. Sorry, could you explain how should I physically think of phi with some interaction parameter for Q?
It is the physical interpretation. It is the shear tensor that you sort of generate in your fluid. It is the product of the shear stress times the shear viscosity coefficient that you have. Yeah.
Why is it A1 just 1? Because we can substitute 3 over the epsilon of the 3 tau into the tau.
Right. Yes. So this was the case where I said I sort of assume phi to be 0. But now I say I want to actually solve these equations for phi non-zero. So you're absolutely right. If I sort of went back and say, oh, but for the case where phi of 0, I know what these are. I can plug them in, and then I get that A1 is exactly -1. That's just saying that this quantity here, if I switch off all these gradients, if I want to set eta to 0, this goes to -1, and indeed it does if I didn't make any errors in the combination. But for arbitrary values of phi, this will be given by this combination here, so we can see what that does as a function of gamma now. Gamma is the argument of this. So gamma here is the inverse. Let's keep it as gamma inverse. The inverse of this is given by this combination here, and you can calculate all of these. Calculating the components of the shear stress is something that can be done. It sort of takes a little bit of algebra, but the main thing is that every time we see one of these sigmas, it's a gradient. All of the gradients here are always going to be proportional to 1 over tau. So we can already write down what this is proportional to, because that's all we're going to need. So it's going to be proportional to eta over epsilon plus p. And then we have 1 over tau squared in the numerator, 1 over tau in the denominator. That's just a single 1 over tau. Eta over epsilon plus p. We can use thermodynamics to say that epsilon plus p is nothing else but the entropy density times the temperature. So we can plug this in here and find that we have the following combination. And then you can say, oh, but if we have a conformal fluid, it is kind of maybe a useful sort of thing to assume this to be a constant. And if that's the case, really gamma is essentially just proportional to tau t. And we're going to sort of try to find scaling solutions of A1 simply in terms of this variable. A1 in terms of tau t. Okay. So my claim is that if we look at A1 as a function of this variable, maybe we find attractor behavior for this and other systems of equations.
Earlier you said that gamma was an attenuation length, but it's unit.
That's right, yeah. So it's an attenuation length over a typical scale of the system. Thank you. So fine, so we have this A1 here, but now what we need to do is we need to actually calculate it. Let's see, so first of all, what do we want to do first? The first thing we want to do is we're going to look at this equation here. Okay, let's just copy this over, and I'm going to divide by, again, this argument here. So we'll find d tau epsilon times tau divided by epsilon plus p is equal to -1 plus phi over tau. But this guy here, the division of this over that, that's just how I defined A1 in the first place. So this is nothing else but A1. So then A1 is -1 plus phi over tau. Oh, divided by epsilon plus p. That's very nicely. So I divide this whole equation by this argument here. So the tau drops out, and I get phi divided by epsilon. What I can then do is I can take the derivative of this with respect to tau. So d tau A1 is then, this thing drops out, then I have two terms here. I have once d tau phi divided by epsilon plus p minus phi divided by epsilon plus p squared times d tau of epsilon. Right. I feel like I don't really have enough board space to sort of go through all the steps in as much detail as I would want to. So let me sort of say what I'm doing. So I'm taking this equation, which is now the first derivative of A1, and I'm gonna sort of look at the right-hand side here, and I'm gonna recognize that I can write the d tau phi in terms of its equation. And every time I see a phi, I will replace it by A1 plus 1. So long story short, on the left-hand side, I have my A1, and on the right-hand side, I will get something that only depends on A1 and eta and tau pi. And I claim this can be done in 4 lines, which I have a hard time fitting in here. So you have to sort of kind of trust me for that. So basically what we find is we find d tau A1 is equal to 1 plus A1 times minus 4 A1 over 3 tau minus 1 over tau pi, and then we have plus eta over epsilon tau pi tau. Again, so there are 3 steps in between. So we are almost where we want to be. So now we have here the derivative of A1 with respect to tau. In principle, that's okay, but we really want to sort of use the fact that A1 is a function of the scaling variable tau t. So we need to replace the derivative with respect to tau as a derivative of this combination tau t. That's fairly easy. The Jacobian is not so hard. Basically, we find that, so what do we have? So this is the same as d tau t of A1 times d tau t with respect to d tau. And this combination here, or this Jacobian here, sort of is basically given by tau t plus tau times the derivative of t with respect to tau. And the derivative of t with respect to tau, we can essentially replace by a derivative with respect to epsilon. The derivative of epsilon we can replace by this equation here. So long story short, we get again a combination that just involves A1. So what you find is that this whole equation becomes the following thing. So what do we get? We get, let me call it A1 prime for the derivative of A1 with respect to its full argument. 1 plus A1 over 3, that's essentially the Jacobian. And then we have minus 1 over 1 plus A1 times 4A1 over 3 tau t plus 1 over tau pi t. And then the whole thing plus 4 eta divided by 3s tau pi t and tau t. Both of these. If we have a conformal system, then we can take tau pi t to be constant. And we can try to sort of look at now the behavior of this equation here in different regimes. So look at different gamma, which means that we're looking at different values for tau pi t. again, to reiterate, if tau by t is very, very large, we expect A1 to just go to -1. Otherwise, we've made an error in our sort of rewriting. But we can look at any value of tau pi t, because that equation is in principle defined for any value of tau pi t, including tau pi t 0, at which case the gradients would be infinitely large. So for tau pi t large, this is small gradients. Look at these equations here. So this is a constant. This is small. This is also small. So basically, since that is a constant, it means that the argument here sort of has to match the left-hand side over there. If the argument needs to match the left-hand side over there, you can check that a consistent equation is that A1 is a constant. In this case, the left-hand side vanishes. And then the result will be that A1 has to start as -1. You can continue the argument and say, what is the first order correction? So you do a correction to this result. This needs to be a result that has a correction term that is order 1 over tau, and that will be something that is 4 eta over s tau t, and then you can go on. You can sort of calculate second order, third order. You can calculate any order in a power series in small gradients that you want to, which basically mean that for these systems of equations, you can write down the full hydrodynamic series, gradient series, to arbitrary number of gradients. Okay? So this is an example where you can solve the hydrodynamic gradient series, all the coefficients, up to order 1,000, if you wanted to. And people have done that. So this is not second order, third order gradients, it's 1,000 order hydrodynamics. And we'll get that whether that's sensible or not at the end of today's lecture. So, fine. So that's, if you want to expect it, it says that for weak enough gradient, the scaling level approaches -1 weakly as 1 over this small gradient correction. Maybe sort of more interestingly, we can look at perturbations around this decoupling regime. And what I mean by that is that we can say, oh, let's look at, let's say A1 is basically given by, let me give it a different name. Let me call this A1 series. Okay? We call this A1 series plus delta A. The delta A is a small correction to this. In particular, I can be very bold. I can sort of truncate the series at its leading order term. So I want to calculate the correction around -1. I can take this, I can plug it into the equations for A that are sort of up here. This is an exact differential equation. I can plug this in. Well, if A1 is -1 plus delta A, here you get delta A prime. If you're expanding A1 around -1, you get 2/3 plus a correction that goes like delta A. If delta A is small, you're sort of ignoring second order corrections. And then on the right-hand side, we have the first term, which is, again, just minus delta A. This term here, again, sort of is small because it's vanishing as 1 over tau. So you're only picking up this term. And then this term is again small because it vanishes as 1 over tau. Now this is a differential equation that you can solve. Have delta A prime over delta A is just delta A prime over delta A is minus 3 over 2 tau pi t, or integrate this up, delta A is proportional to the exponential of minus 3 over 2 tau pi t. Minus oh, we're integrating all this over, yeah, very good, thank you. We're integrating over tau pi t, so that is missing here, and tau pi t. So if you want to, the t cancels out, which is the same as e to the minus 3 tau over 2 tau pi, for instance.
So the variable that you are considering the E1 would be a function of tau times t.
Yes.
And the prime is e by e tau t.
Right. All the primes always miss in differentiation with respect to tau t. I'm sorry if I haven't explained this. So I did this change in Jacobian here, and this d by tau t, that's basically that's what I mean by prime. Okay. Sorry for the confusion.
On the question.
Yes.
How is the condition of tau pi t equals to constant arising from? Is it a result I should assume for conformal?
Yeah, you can assume it for conformal systems. Yeah, by dimensionality essentially. So conformal systems don't have, well, every dimensional object in conformal field theory is scaling by its trivial mass dimension. Tau is a length scale, so it has mass dimension -1. So in order to have a dimensionless combination, tau pi t will then not be dependent on any of the dynamical variables. Okay, so we get that perturbations around the series solutions have this particular form, which you can see is dying off exponentially with respect to tau. Okay? This is e to the minus tau times something. So put differently, if I
So you have perturbed around the series expression,
yes.
but you solve for the evolution of the perturbation under the assumption that tau times t is
That's right. Yes. Yeah, that's right. So exactly. Very good. Yeah. I'm solving the equation. I'm solving perturbations around the series in the late time limit where the series is sort of set. So what that means is that if I sort of make a plot of A1 as a function of tau t, we know that it sort of goes to -1 where tau t is infinity. We also have a correction here, which says that for tau t is not exactly infinity, but so it's less than that. There's a positive correction that sort of looks like this. That's the first order series term. And then we find that perturbations around this sort of have solutions that are proportional to this exponential. Presumably they come with arbitrary amplitudes. So what it means is that if I were to sort of actually solve A1 from this equation with a given initial condition, I would presumably be not on this line. I would be somewhere else. But I know that the perturbation of this around that decays exponentially. So what I get is something like this. And once I'm close, I'm exponentially close, and I don't leave the curve anymore. I do it with a different initial condition. It'll look like that. I can start above it. So in this sense, this curve here that we're calculating is the attractor for arbitrary initial conditions, because it can show that arbitrary perturbations around it, at least in the late time limit, decay exponentially. So that's why A1 is called an attractor. Okay.
So
Question.
initialize also actually large values of tau.
Yes, right. So all I've done so far is assuming late times. I can do better than that, but yeah.
You started out by drawing this line and looking at the first term that is slopes, but the attractor is the entire series.
That's right. So maybe sort of my plot was
something slightly different than the first term.
right, so let me sort of do something different. Let's go way to the left. My line is really over here. And all I've done is sort of at late times, okay? I have nothing about early times yet. But let me do that now. Okay. Actually, let me make one more comment before I go there. Okay? The comment has to do with how this exponential decay actually goes. So we have e to the minus, and I like the other form, 3 tau t. Actually, it doesn't matter which form. 3 tau t divided by 2. That's how we find this thing is decaying. Recall that for the second order hydro theory that we looked at, we found this extra non-hydrodynamic degree of it. It's called omega nh,
and was given by minus I over tau pi.
Now, if we did a normal Fourier transform of something into real space, then usually we are used to think that a quantity, let's call it Q, as a function of time, is given by e to the minus I omega nh t, and then maybe some time dependence. And that's just saying that, okay, this is how this frequency sort of tells you how things are. However, this is flat or non-expanding spacetime. Non-expanding. The way that we usually sort of call this, we say that this is in a box. It's a box, the box doesn't move, there's nothing happening. Here what we're doing is we're doing something where the box is stretching because we're in a space-time that's expanding in one dimension. So I claim that the corresponding formula that you should write down in the space-time that's expanding doesn't look like that. It says that Q of tau is equal to e to the minus I integral d tau of omega. If you had sort of trivial dependency, if this was just time, you just get back to what your formula sort of says. But let's look at what happens if you have a space-time that's actually expanding. We know that this is the formula for tau t, so it's e to the minus integral tau. So we have minus I times minus I, that's just minus 1. So that is the minus that we have here. And this is just 1 over tau pi. 1 over tau pi, I can write this as 1 over tau pi t divided by t divided by tau pi t, but t is the temperature. If I am at late times, the temperature sort of scales like tau to the minus 1/3. I can plug this in here and find that Q will scale as e to the minus integral d tau to the minus 1/3 times tau pi t, which I say is a constant, because that's what my conformal theory tells me. So I have to integrate tau to the minus 1/3 in the exponential, and this is given by e to the minus tau to the 2/3 and 3/2 tau pi t. And tau to the 2/3 is nothing else but temperature times tau. So I can replace that by tau t. And then I want you to sort of compare this result here with respect to the solution that we found for the perturbations at late time. So there's an exact matching between the die-off of the perturbations, how they die off quantitatively with time, and the non-hydrodynamic mode dispersion relation that we found by completely different means. So what this is supposed to be showing is that the non-hydrodynamic mode dispersion relation is controlling the exponential fall off of what you have in your theory. Okay? Even if you are in a system that's not static. Okay? So we calculated this in a static system at equilibrium, but here we have a system that's expanding in one direction of space-time. It's fully nonlinear, but still the die-off is given by exactly this mode. Let's see if there's some questions up to this point.
So you substituted t to the 1/3 with t, but that's like the ideal solution. So
Yeah.
are you suppressing higher order?
That's correct. So what I'm saying is that I'm doing this again for late times where tau is approximately given this plus higher order corrections. You can try to include the higher order corrections, and people have done that, and you find that also those match. So even for more complicated theories, you can push this very far. You find basically complete agreement between how the perturbations sort of die off and the non-hydrodynamic mode spectrum of your theory. So really, these guys tell you basically how you approach this A1 solution that we talked about. Further questions? Because I'm going to delete something here.
Isn't this a bit So maybe a generic question.
Yeah.
Generic. Isn't it a bit by hand, right? I mean, how pi was put in by hand and sort of standing for the more detailed microscopic theory. So really it's, and we discussed it with Chandra though at some point, right? This is the difference. You have this exponential diode of this non-hydro mode, and certainly it's faster than power law diode of your, say, energy densities, right? And that's why the exponential diode catches up to the attractor curve faster than the attractor curve also time. So if somehow instead of this tau pi system, there was something non-exponential, which may not be, of course, the truthful representation of underlying dynamics, but a priori we don't know, right? So if there was some other mechanism, would there still be an attractor, or would you be in a situation that the approach of all the different starting curves to the attractor would be so slow that there would never be a conversion? It would be as slow as the attractor going to negative pi.
Yeah, so the question is that an accident? Is it by hand, or is that more generic? So in this case, while I would argue that there is some generic nature to it, I agree that the mock microscopic theory that I've written down and conveniently erased is not very sort of deep. However, what I can say is that you can do exactly the same program, and I will show you some of this, for a system that's much more complicated, which is the same broken flow, but for n equals 4 super beam, there's an infinite coupling, where the exponential, but the approach to the attractor is oscillatory. So it sort of oscillates around the attractor, and you can find the matching between the approach to the attractor and the quasi-normal mode of the corresponding non-hydro mode to 7 digits. And you cannot find only the first one, you can find the first 8 ones. So there are 8 non-hydro modes, there are an infinite number of non-hydrodynamic modes. So, okay, the short answer to your question is that it holds in general as far as we can tell. There are quite non-trivial cases where these checks have been done, which are more complicated than this. You don't have to be just purely exponential. You don't have to be power. You don't have to sort of have this particular sort of a simple sort of just single pole in the system. It holds more generally than that. But no, even in kinetic theory, the coupling is small. So right. So I think all I'm saying is that okay. So while at this point, okay, it's perfectly fine not to be completely impressed. There are more complicated things where you can check the same thing and you find the same nice agreement. But for these lectures, I will only sort of present one of these examples, which is n equals 4 super. Yes.
It's not clear to me how the non-hydro mode controls the decay of the perturbations.
Yes. So let me see, what do I need? I want to sort of be, okay, I can delete this. Okay, so very generically, if, oh yes, let me sort of take my example of the diffusion equation again. So where, so if I want to calculate perturbations, for instance, around the current, I can write this down, at least in linear response, as an integral over the 2-point correlation function times some source. And this is, if this is the Green's function, this would be integrated over, in particular, the omega, and it would have e to the I omega minus I omega here. Now, this thing here is the 2-point function of the correlation function. This is basically the structure of these collective modes that we have. I can make a plot of this function, plots of jj in the complex omega plane, where this is the real part of omega, this is the imaginary part of omega, and I will have certain analytic structures in this 2-point correlation function. In particular, I will have modes that are, I call hydrodynamic modes, And I will have a pole like this, which for instance sits at omega is -1 over tau. This is this pole here. So then if I, right, top pi, fine, okay. So if I if I want to calculate what the actual response is, I have to sort of do that integral here. This runs from -infinity to +infinity. I can do that by sort of closing the contour, the lower half plane. So I pick up all the analytic structures that I have. And in particular, I will pick up this pole here. So I have to evaluate the integrand here at this pole. And what you find is that this sort of goes like essentially the residue of this, let's assume this is sort of easy, times the source times e to the -i omega t evaluated at that pole, and that -i times -i is just -1. We get minus t over tau pi. That's generically how these non-hydrodynamic modes control the exponential sort of approach of perturbations to some other sort of location. Was there another question, or was just it one? Okay.
On the formula on the right, where A1 is -1 plus delta A.
Yes.
Should we write A1 equals to -1 plus theta over x by tau t plus delta A? I mean, the part of the first order solution, not in the zero.
Right, and the answer is it depends on what you want to perturb around. So I perturb just around the -1, but of course you're free to perturb around the first two terms. This first part here will not change, but you will get corrections to this, and the corrections will be sort of whatever sort of you are perturbing around. The correction may get more complicated.
So by doing that, you will be able to move a little bit further to the left.
Right.
Here.
Yes, that's right. So we could move further to the left, but we can do much better than that, and I still want to get to this, unless there are some other urgent questions. Okay, so far as has been remarked, all of this discussion has been for large enough time such that I can do a series expansion or perturb around this series expansion. Now let me sort of try to do the complete opposite. In principle, there are various ways to do that. Okay, so this is a ordinary differential equation. I could just sort of solve this numerically and see what it does. And basically what you find is that yes, this attractor here actually sort of extends to early time, and there is this exponential sort of approach happening also at early times. In order to sort of get an analytic understanding of what's going on, we can sort of use a technique that's borrowed from cosmology, which is called a slow low expansion. The idea being that if we have an attractor curve, in particular at very large gradients, then that curve basically should be something that has a special sort of structure in terms of this A1. So putting it around, if there was no attractor, this curve in principle you would expect goes either to infinity or to 0, does something very bad, in which case the derivative here would be very large. So let's just sort of try to solve this equation by sort of doing a slow roll expansion of the system now for very, very early times, so small tau t, which brings us all the way to the left of this diagram. So slow roll. A1, 0, at leading order, we sort of assume to be 0. And this whole left-hand side vanishes. This right-hand side is equal to 0. It turns out to be a quadratic equation. So let's see, the equation sort of looks something like this. 1 plus A1 times 4A1 over 3 tau pi t plus 1 over tau pi t is equal to 4 theta over 3 tau pi t power t. We want to solve this for very early time, so we want to multiply this whole expression by tau t and solve for A. And we can do it. So it's a quadratic equation. You can solve it, and I claim that if you solve this quadratic equation, you find that A1 sort of goes like, or is equal to, minus 1/2 minus 3 tau t over 8 of pi t plus square root of, sorry, there are two solutions, but only one of them sort of corresponds to our attractor. 64 e over s for pi t. It's a complicated expression. It's a complicated expression that involves tau pi t and e over s and tau t. The main point of this is that this is well defined for all tau t from 0 to infinity. And if you plot it, sort of starts at some value, maybe here, then nicely sort of approaches the curve we had before. It's not exactly equal to this series truncation, but it's close by. And it has the property that if you were going to go back to your differential equation to solve this numerically for arbitrary A1, it actually has the same property that curves sort of approach this unique solution exponentially quickly. I'm not sure who was first. Yeah.
Under the radical,
yes.
So tau pi t in the denominator? Or
Yes, so there's tau pi t down there, and they're also in the argument. That's what you're asking. Yes. Okay. So don't pay too much attention to the explicit expression, because essentially I sort of, by writing down this first equation that I said was my mock microscopic theory, I threw away a bunch of terms that ordinarily you want to keep. As always, the full equation and solution is in the book.
But the approach is only exponential as long as tau is not. And
That's correct.
When you go below, it
Yes.
becomes tau alone.
That's right. Yes, that's right. Yes, there's
Very,
an
very
approach.
many times the character
That's
changes.
correct. There's an approach, but the approach really sort of only becomes exponential in the regime where tau pi t is much larger than, no, the other way around.
Tau is larger than
Exactly. Yes, thank you. Tau is larger than tau.
Sim A1 prime is about 0.
Yes.
Large tau t.
Right. So I assume this. So basically, it's an assumption. Or it's an approximation. Then I get an equation that I can solve. Initially, I've made this assumption to get at the behavior at early times, but it turns out that the resulting solution that you get is well behaved for all tau t. So I'm basically sort of saying, okay, let's just look at the solution for all tau t, and you find that it's well behaved. Okay? It's an approximation, so you could say, okay, but now let me sort of calculate corrections to this. And the way you would do it is to say, okay, you can sort of say, let me call this A1 star. Okay? And go back and say, now A1 is A1 star plus delta A, and I want delta A prime to be 0, but I don't require A1 star to be 0. So then this is second order slow roll. And you can do the third order slow roll and so on and so forth. So you can do something that is similar to a gradient expansion, but it's not a gradient expansion, it's a slow roll expansion. It has the same issues as the gradient expansion. So the upshot is that this is an approximation, but it nevertheless sort of captures the physics that there is really sort of this attractor curve. And this attractor curve, to which sort of all initial conditions sort of approximate to, generically can only be precisely determined numerically. Take this ODE, solve it for different initial conditions, and you find the one, so you sort of scan initial conditions, and you find the one where basically the small perturbations away from this thing don't decay back to your attractor. This is a very, very good analytic approximation. Works to a few % accuracy typically, but it's not the exact. Okay, let's see, questions. Yeah.
So this the pattern that comes in the exponential as this power of the power of follow is more than becomes crucially on the value of the
Right. Yes. Yes. So as was pointed out, again, so the late time approach is exponential, but in particular the approach to this attractor, let me just say, need not be universal. Okay, so it can be dependent on all sorts of other things. The attractor is, but the approach to the attractor need not be universal. It needs to be fast, but not universal. Well, you can even sort of change it such that it becomes. So if one plays games and sort of makes the interaction weak enough, then you can actually sort of lose the attractor completely. But for, in particular, this conformal case here, where tau t is a constant, that's basically been resolved.
What do you mean by the attractor being used, the existence of the attractor? But if you change the equations of motion somewhat away from what you started out with, which is this particular evolution equation for the phi, by using some different sort of dissipative hydrodynamics, so then this function will be.
Right. So if you change your microscopic theory, then the attractor changes. That's correct.
Okay.
Yes.
If we don't assume conformal symmetry, is the Bjorken flow still there? And do we still have an attractor? Is the conformal symmetry a must?
Very good question. So the question was whether if we have a system that's not conformally invariant, whether A, Bjorken flow works, and B, whether the attractor is still there. And the answer to both questions is yes. You can do Bjorken flow for any system. Non-conformal systems is not a problem. And B, yes, you still have an attractor even in non-conformal systems. And I wrote a paper about that. I don't remember neither the title nor the preprint number. But I think it was 2017, October 2017. So that's all I can say. Any more questions? Okay, very good. So then let me just finish by saying that, so I've outlined sort of this attractor here, that it sort of exists in this microscopic theory. So really what I still had wanted to do today, but we'll do at tomorrow's lecture in the beginning, is that I want to connect this to this whole idea of Borel resumming a divergent series. So that's what we're going to start to do tomorrow. And then we're going to transition over to this relation between hydrodynamics, kinetic theory, and ADS-CFT, which, if I keep saying this, sort of remind me that most likely I won't get to all of these, but I will do my best. Thank you very much for today, and I'll see you tomorrow. Oh, I have 50 minutes. Oh,
That's true.
very good. Hey, great. So then we can still do this. Yes. Okay, very good. Thank you for reminding me that I still have 15 minutes. It's always good if you get extra time. It's never good if someone tells you, oh, you should have finished 15 minutes ago. Anyways, good. Very good. Okay. So, fine. So we get these attractors. To sort of set the stage, let me just say that for this system that I just outlined, I said you can calculate 1,000 orders in this gradient expansion. And you can do this and you can plot the value of these coefficients, and you'll find that the value of these coefficients basically sort of increases essentially factorially as you sort of go to a higher number. And that typically is a sign that the series, the gradient series that you have, is not a convergent series, which well, most physicists sort of have trouble sort of putting into finding what the consequence of this is. Okay? So let me just sort of start by saying something about a convergent series. Okay, yeah. Oh, I used the wrong mark. What is a convergent series? Okay. The convergent series is, for instance, a series f of x e to the x, which I can write n is 0 to infinity, x to the n over n factorial. This is a convergent series because I can for instance, get to the function that I want to sort of approximate by sort of taking a number of series terms, and the number of series terms that I need to sort of get to my function here is finite, and the result improves as sort of add on more of these terms. Okay? In particular for this series here, let's just do an example of f of x versus x. If I start with the leading order terms, this is 1 plus x squared over 2 plus so on and so forth. So we get 1, and we get 1 plus x, and we got 1 plus x squared, and so on and so forth. The main point being that even if I wanted to sort of evaluate this at, for instance, x is 1 or any other number, I can get there by basically sort of adding sufficient number of terms in my series, and the result will gradually converge to that expression. So in that sense, it's a convergence series because you can sort of take n terms and it converges to the result here. So that's fine. This series is particular in the sense that its radius of convergence is infinite. So that means that for this particular function, there is no limit to how large you can make x. The result will always converge to the right answer if you add sufficient number of terms. However, in practice, the number of terms you need to get the series converged at x is 100 is staggering. Okay, but in principle, it can be done. Okay? Another example for convergent series is f of x being 1 over 1 minus x. So that's 1 plus x squared over 2. No, not x squared over 2, just x squared. Thank you. Plus and so on and so forth. So this is just sum n is 0 to infinity x to the n. And this series has the property that its radius of convergence is not infinite. It's basically given by the first pole that you encounter in this form here, which in this case sits at x is 1. Okay? So you would say, okay, I mean, so far we have not learned very much. Okay? And I would agree. However, now let me sort of give you a different series. Let me sort of write down a series that is, what series do I want to do? Okay, I want to do this series. I don't know why I didn't want to do this, but n is 0 to infinity minus x to the n times n factorial. Okay? So the minus 1 is harmless. You just change x to minus x. It's just a function 1 of x. But what I've done here is that I have multiplied each coefficient by n factorial. Okay? So this series is 1 minus x plus 2x squared minus 6x cubed, and so on and so forth. This is an example of a divergent series. So what it means is that if I were to plot different orders in this setup, what do I get? The first term is 1. So okay, this is this exponential, but whatever, I plotted on the same plot. So you get 1 for the first order, then you get minus x for the first correction, then you get plus 2x squared, then you get minus 6x cubed. So basically you get something that as you add each order, not only do you not converge to an answer, you seem to be moving farther and farther away as you add orders because the corrections always get larger. Okay? So if I were to try to find the value of the function at x is 1 from this series here, good luck doing it. Okay? So you won't converge to anything. The result will sort of change and flip sign as you sort of go on and add more and more orders. So that just means that the series is divergent. So you might say, okay, I mean, wherever do we have examples like that? That seems like a contrived case. I would agree that's a contrived case, but then I might remind you that if you do perturbative QCD, you're exactly in this case. It's a divergent series. As you add orders, the series will not converge. It's a divergent series. It may be asymptotic in the sense that, okay, maybe we can't calculate 1,000 orders. Maybe you can only calculate 4. And maybe that's good enough to get a result that's reasonable for very, very small results of our axis, where x is now for QCD is g. And maybe it's true, or maybe it's not, but you're in this regime, okay? The same is, of course, true for QED. The same is true for the anharmonic forced oscillator. The same is true for lots of examples in quantum chemistry, turbulence. People have argued that all physically interesting examples have perturbative series that are divergent. I'm not sure if that's true, but it's.
That's what makes it interesting.
But yes, so I mean, one could make an argument that there are some interesting examples, for instance, such as QCD, that definitely fall into this class of problems. Okay, so what do you do? Okay, so you have a series. You can, in this case, calculate arbitrary number of terms. What is the answer? In principle, it's a measurable quantity. You could ask what x as a certain function is, but we don't have an experiment to directly get it.
So just a minor comment of QCD, the series of sign alternate.
Right, the sign altering. So I can do the same series, but do a plus.
Yeah,
it's still divergent. Yes.
that's what you have.
Right. Yes, but that doesn't change the nature of the convergence of the series. It's still. And we'll get to Borel summatability. It does not change the statement that it's a divergent series.
Okay.
So what do you do in this case? One of the methods that we can sort of try to use is the so-called Borel transform, since it was just mentioned. Let's do that. Actually, to get started, why don't we have that much time? But why don't we get started by talking a little bit about a Borel transform first for a convergent series to sort of convince ourselves that what we're doing is not black magic and leads us completely astray. So what is a Borel summation? Let me use the wrong marker. Borel summation. It says that you take your series F, that is, you have a series that you want to sort of treat. And you calculate the Borel transform V of F of X, which is defined as your original series. Let's take, why don't we take this conversion series first to get started? So we take the initial series X of n divided by n factorial. Sorry, the point is that you take your initial series and you divide each coefficient by n factorial. So everywhere we had a coefficient alpha n, you divide by n factorial. That's how you define the Borel transformation. If you do this, then okay, this series I think is what I sort of have written up over here. So this is nothing else but e to the x. And as such, it has nothing to do with the function that you actually sort of started out being interested in. Okay, but what you can do is you can do an inverse Borel transform of this. Okay, it has to start from 1 and has to start from 0. Thank you. So you can do the inverse Borel transform of this, and I will call this F Borel of x, and it's defined as the integral Vz 0 to infinity e to the minus z of the Borel transform of F equal to x z, product of x and z. So for this case here, find that this is the integral Vz 0 to infinity e to the minus z. The Borel transform was e to the x. The Borel transform from argument x z is e to the x z. So then these two together are e to the minus z times 1 minus x. We can integrate this. It's the integral over an exponential. Even I can do this. Then we find that we integrate this, we have to divide by 1 over 1 minus x, and we evaluate this from infinity to 0 to the infinity, so it's 0, and at 0, we start canceling the minus there. So I claim this is the result that you get from this integration. And the point that you should notice is that what we get out here is what we started out from for a convergent series. And you can sort of see also the radius of convergence, because I sort of integrated over this, sneakily sort of assuming that x was smaller than 1 in order for this integral to be defined. That's a question.
Yeah, C is in general complex.
That's right. So right now it's just an integration over the real, positive real x's, but eventually we're gonna study cases where it's complex. Yes. But right now, this is just the standard Borel transform. Where Z is just, you're integrating along the real axis. No big deal. So fine, the point of this exercise was to show you that if you take a convergent series, you do a Borel summation of it, and then you do the inverse Borel transform, you get back the series that you started with, okay? If we hadn't gotten that, it would be better to sort of tell me that I should retire or something. Now, you want to sort of use this not for this convergent series, but you want to use it for the divergent series. Where I said that you can't really make sense of this expression at all. So same exercise. Our series here looks slightly different. So we're going to take the series as it is defined. So we have minus x to the n, but now I divide all coefficients by n factorial, so the n factorial just drops out. And by virtue of constructing this example, this is exactly the series that I wrote down earlier, except for the minus sign. So this is something that I can write down in closed form. I think this is true. And again, you might say, well, I mean, this has nothing to do with the original series. It's a completely different function. And I would say, yes, that's right, but we have to do the inverse Borel transform to see what's going on. So let's do this. We have to calculate the following integral. The Borel transform is given by 1 over 1 plus xz. Now, question to the audience, what is that integral? Students first. We'll work our way up to the full professors, as usual. Yeah, don't look it up. I mean, it's not fair. Some exponential integral, that's pretty close. So it is 1 over x, e to the 1 over x, gamma 0, 1 over x. The gamma is incomplete gamma function. Also known as some form of the exponential integral. And you stare at this expression, it's a very, very complicated expression, which I would never have guessed, but comes out. But the magic is that if I take this expression and I do a series expansion of this expression for small x, I find that this is equal to 1 minus x plus 2x squared minus 6x cubed, blah, 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 equal to sum of minus x to the n factorial. So it has the same series as I started up with, but it's now a closed form expression.
By small x, you mean like x is smaller than 1?
Yeah, x is dimensionless, x is small. So you would say, okay, fine. I mean, maybe we haven't gained much. We just got a funny function out of it, but maybe the function is just as ill-defined as what we started out with. So let me plot on the quotes what the function looks like if I find the red mark.
Going back to, so when you write the Borel transform, that series, the sum is 1 over 1 plus x. So doesn't that say that in order to do this Borel transform, x should be smaller than 1?
So
you can write down that series up there. Say 1 over 1 plus x is the sum of that, which implies everything's of 1.
Right. So
So
your
the
question is,
solution only works for x smaller than 1.
so your question is about the analytic structure of the expression that I wrote down. Over here, you're saying that that expression has a pole of x is -1, and I should be careful about mod x. Your question is perfectly oriented. So we can definitely sort of do the summation for x absolute value being less than 1. But in order to plug it into the Borel transform, we're going to analytically continuate for all x. And that's a critical point. But as long as we don't hit the pole,
I would claim it's perfectly fine. If we hit the pole, we have to do something more clever, and that will sort of bring us to generalized Fourier transforms, which then sort of mean that we have to take.
When you do this interval along your contour has to be on the pole.
Correct. If we happen to have done this with a different set of x, the pole would be on the positive real axis, and we would have to deform our contour to avoid running into the pole. We'll talk about that, but let me just finish off that exercise here by saying that we got this funny function from this Fourier transform. Let's just look at what that function looks like. Okay? So I said that if I plot 0th order, 1st order, 2nd order, 3rd order, I just get this fluctuating junk. But if I plot this function, I get infinity, no. Okay, I have to use black, I apologize. If you plot this function here, you get something that's well behaved for all values of x. So you get a nice, well-defined solution that doesn't diverge anywhere in the whole interval x from 0 to infinity, doesn't flop around, so you can evaluate it at each of this point. And I would claim that it's this function that's really meant by this divergent series, even though I can't make a sense of the series by truncating it any finite order. So this is what Fourier transformation does for you. Okay? Sort of give some meaning to the divergent series. And I stress that it's some meaning because there is generally no proof that Fourier transform that you get out is unique. It's some meaning of the divergent series. But it's better than having a series that you can't use to sort of really calculate anything in the first place, I would have. That was a question.
So then one condition for Fourier summation is that it grows slowly.
That is correct. Yes, you need to have a series where the coefficients grow slower than n factorial, otherwise it's not Fourier sum. Yes. So it doesn't work for all divergent series. It works for a restricted class of divergent series.
It grows slowly.
Yeah, n factorial is just fine. If it was n factorial squared, I would be in trouble.
But then we can do it double.
Yuri wants to do a double Fourier transformation. Maybe.
You actually read the original book.
Okay. Yes. So Yuri says there are cases where you can do it. So all I'm claiming is that this technique, as advertised here, only works for series where the coefficients don't diverge faster than n factorial.
So this is running a little bit, but presumably you want to apply this to gradient function hydrodynamic. I guess two questions. A, do we get this sign alternating series or non-sign alternating series? And therefore, whether you pole E's on the positive real axis or negative real axis. And if the pole is on the positive real axis, in two theories, sort of consensus that there may not be a right hand to go around the pole, whether the same issue arises.
Yes. So Yuri is asking.
To answer it tomorrow.
Right. Yeah. Basically, Yuri is asking a question which I will answer tomorrow. But let me just say that the answer to this question is that yes, generically you will find that for hydrodynamic series there is a pole on the positive real axis. So you have to sort of define a contour. The contour will have an ambiguity, and the ambiguity, you can figure out that the ambiguity is just the piece of the non-hydrodynamic mode that gives you the exponential or decay to this hydrodynamic attractor. The details are from right tomorrow. Okay, thank you very much. We are over.